Welcome back to the Deep Dive. I want to start today with a scenario that I think we've all just sort of accepted as normal. But if you actually stop to think about it for a second, it's kind of absurd.
I love absurd. What have you got?
Okay, so you're in the back of an Uber.
Right.
You're moving at, say, 40 miles an hour down the highway. You pull out your phone, and you decide to stream a 4K video.
Mm-hmm.
And it just works. No buffering, no pixelation. You're pulling down gigabytes of data from the air while physically moving through space.
It is pretty remarkable when you frame it like that.
But here's the thing. I was looking at the basic specs for a standard radio signal.
Mm.
And statistically, that shouldn't happen.
Yeah.
A single radio wave just shouldn't be able to carry that much heavy cargo that quickly. So my question for you today is the network lying to us?
Lying.
Yeah, like, is it doing some kind of compression trick? Or is there something happening physically that we just aren't seeing?
Well, it's not lying, but it is definitely cheating. Or, well, maybe cheating is the wrong word. It's teaming up. See, you're assuming the network is sending you that 4K video over one single radio connection.
Right. One cell tower, one signal directly to my phone.
And that right there is where you're wrong. What's actually happening is a technique called carrier aggregation.
Carrier aggregation.
Exactly. It's arguably one of the most critical features in modern LTE and 5G networks.
Okay, so we have a massive stack of source material today. I'm talking technical architecture diagrams, protocol stack layouts, deployment foundation docs for both LTE and 5G NR.
Lots of acronyms in those docs.
So many acronyms. And I see the term CA all over them.
Mm-hmm.
But we just strip away the jargon for a second. What is this actually doing? Our mission today is to figure out how networks are basically widening the highway for all our data.
Think of it this way. If you need to move 1,000 people from point A to point B, and you only have one bus...
It's going to take forever.
Right, it's going to take forever.
Yeah.
You can try to make the bus drive faster, maybe put a bigger engine in it, but there's a physical limit.
Sure.
Carrier aggregation is the network manager stepping in and saying, don't just use the bus and that train over there and this fleet of taxis and send them all at the exact same time.
Wait, so my phone isn't just listening to one frequency, it's listening to, what, 2, 3?
In the 5G era, it could be listening to bits and pieces of up to 16 different frequencies simultaneously.
16.
At the same time.
Theoretically, yes. It stitches them all together instantly.
Yep.
So to you, the user watching that video, it looks like one massive high-speed data pipe.
But underneath?
Underneath, it's actually this Frankenstein monster of different radio waves.
Wow. Okay, that sounds incredibly difficult to pull off physically. I mean, just trying to tune an old FM radio to 2 stations is hard enough. Tuning to 16.
It is an engineering nightmare, frankly,
I'll bet.
but it's totally necessary one. And to understand why they go through all this trouble, we have to look at how spectrum actually works in the real world. You can't just go to the store and buy a huge, perfect block of 5G.
Right, because the government auctions it off. Exactly. And spectrum is incredibly scarce. It's like real estate in Manhattan. You might buy a plot of land here and then a tiny plot of land 3 blocks away and maybe another one way across town.
So it's all broken up.
Yeah, you rarely get a massive contiguous field to build your skyscraper on. So network operators end up with these fragmented bits of frequency, some down at 700 megahertz, some at 2.5 gigahertz, some way up in the millimeter wave bands.
So carrier aggregation is basically a survival strategy.
Pretty much.
They have to glue these broken pieces of land together to build a big house, because that's all they have.
That's a great way to put it. It's about making a coherent whole out of highly fragmented parts.
All right, let's get into the mechanics of this, because the documentation outlines 3 specific flavors of this aggregation.
Yes, the 3 types.
And looking at the diagrams we have, they seem to range from fairly sensible to entirely chaotic.
They definitely get progressively more complex.
Let's start with the first one. It's called interband carrier aggregation. Inter meaning between. So this is combining totally different bands.
Right. This is like combining a low-frequency band, say 700 megahertz, which is really great for distance and range,
Right.
with a mid-band frequency like 2 gigahertz, which carries a lot more data but doesn't travel nearly as far.
Wait, pause there. Those are wildly different frequencies. Physically, the waves look completely different in the air, right?
Yeah.
One is long and rolling, and the other is short and choppy.
Exactly.
How does the phone handle that?
That's the catch. Your phone essentially needs 2 separate pairs of ears. It needs an RF front end, a radio frequency receiver that can tune into the low band and the mid band simultaneously without them interfering with each other.
That sounds like a recipe for massive battery drain.
It absolutely is. And heat.
Yeah.
You're powering multiple receiving chains at once. But the benefit is huge.
How so?
Because it gives you the coverage of the low band so your signal doesn't just drop the second you walk into a concrete building, but you still get the speed of the mid band. It's the best of both worlds approach.
Okay, so that's interband, building a second separate highway. The next one seems a bit more straightforward. Intraband, contiguous CA. Contiguous meaning touching.
Right. This is the cleanest scenario. Imagine an operator gets lucky and buys 2 blocks of spectrum right next to each other. Say, Block A and Block B, both sitting right there in the same frequency band.
So it's just widening the existing highway.
Pretty much. Instead of having 2 separate lanes with a grass median in between them, you just pave over the median. You reduce what they call the guard bands.
The guard bands.
Yeah, the safety buffer of wasted space you usually need between signals so they don't crash into each other. You pave over that and just treat it as one big fat pipe.
I assume that's a lot easier on the phone's hardware.
Much easier. You only need 1 local oscillator, 1 radio chain. It's highly efficient and super common in mid-band LTE. But as we discussed with the Manhattan real estate analogy, operators aren't always lucky enough to own touching blocks.
Which brings us to the third flavor, the tricky one. Intraband non-contiguous.
Ah, yes, the Swiss cheese scenario.
So this is where you own spectrum in the same exact band, but there's a gap right in the middle.
Yes. Maybe a competitor owns the block in between yours. Or maybe that middle slice is reserved for some satellite use. Whatever the reason, you own the left slice and the right slice, but definitely not the middle.
So you have to aggregate across that gap. You're using 2 separated lanes on the same road.
You do. And this is tricky because you have to filter out that middle guy. Your phone needs to listen to the bottom and the top of the band, but strictly ignore the loud signal shouting right in the middle.
I'm just imagining trying to listen to 2 people whispering on either side of me while some guy with a megaphone yells right in my face.
That's actually a perfect analogy. And if your filtering isn't perfect, the guy with the megaphone totally drowns out your data.
And the phone needs to be smart.
It requires very sharp, very expensive filters in the device. This is actually why not all phones are created equal. A budget phone might look at that fragmented spectrum and say, I can only do one of these.
And a flagship phone.
A $1,000 flagship phone will say, I've got the filters for this, I'll take both.
So when I see gigabit LTE or 5G printed on a phone box, it doesn't really tell me if the phone has the actual gymnastics capability to use the network to its fullest.
Not really, no. That's all hidden deep in the modem specs that nobody reads.
Let's shift gears to the numbers because this is where I got totally stuck in the source material. We're comparing the older LTE limits to the newer 5G NR standard. And I knew 5G was faster, obviously, but the scale of difference in this aggregation capability it's barely comparable.
It's not a linear upgrade at all. It's exponential.
Walk me through the LTE constraints first. What were we dealing with?
So in the 4G LTE world, the maximum width of a single carrier was 20 megahertz. That was the standard building block.
20 megahertz. Okay.
And the specs allowed you to combine up to 5 of those blocks. So 5 times 20.
100 megahertz total. That
Yeah.
was the absolute speed limit.
Yeah. That was the absolute theoretical ceiling of the pipe for LTE. And for a long time, that was amazing. That 100 megahertz is what gave us mobile video and app stores. But then 5G walks in.
And just breaks the scale entirely.
Completely shatters it. In 5G sub-6 gigahertz, which is the standard mid-band 5G most people are using around town, a single carrier isn't limited to 20 megahertz anymore. It can be up to 100 megahertz.
Wow. So one single block of 5G is equal to the entire maximum fully aggregated capacity of an LTE network.
Yes, and it gets crazier. If you go up to millimeter wave, that super high band stuff you get in crowded football stadiums, a single carrier can be 400 megahertz wide.
And you can still aggregate those.
Oh yeah, you can aggregate up to 16 of those component carriers in 5G.
Do the math for me there. That's massive.
We're talking about potentially gigahertz of total bandwidth. It's literally like going from a garden hose to a municipal water main.
That's a huge leap.
It is. But there's a nuance here in the 5G specs that's honestly even more interesting to me than just the raw speed. It's this concept called flexible numerology.
Yes, I saw that term in the Foundation docs. It sounds like astrology for engineers. Like your numerology is rising in the house of Saturn.
It does sound like that, doesn't it? But it's actually pure physics. In LTE, the grid of the signal was completely fixed. The subcarrier spacing was always exactly 15 kilohertz. It didn't matter if you were in downtown Tokyo or a cornfield in Iowa. The grid was the grid.
Just a one-size-fits-all approach.
Right. But 5G is designed to do everything, from connecting a low-power smart toaster to performing real-time remote surgery. Those are wildly different needs. So 5G allows the network to actually stretch that grid.
Stretch it how?
You can have 15 kilohertz spacing, or 30, or 60, or even 120 kilohertz.
But why would I, as a user, care about the spacing of the subcarriers on a grid?
Because of time and physics. A wider spacing, like 120 kilohertz, allows for much shorter transmission time slots, and shorter slots mean lower latency. So if you're doing VR gaming or mission-critical industrial work, you need that wide spacing for instant reaction times. But if you're just covering a massive rural area with low-frequency data, you use the narrow spacing. 5G lets the network literally shape the physics of the wave to match the job.
That's fascinating. So where LTE was just rigid, 5G is totally elastic.
Precisely. And that elasticity applies to the device side, too. If you look at the diagrams, there's a concept called bandwidth parts. This is honestly one of my favorite upgrades in the whole architecture.
Is this the solution to the battery drain problem we talked about earlier with all those antennas?
It is. In LTE, if the carrier was, say, 20 megahertz wide, your phone had to physically listen to the whole 20 megahertz. Even if you were just receiving a tiny kilobyte-sized text message, your modem was powered up and processing the full width of the channel.
That's like opening a massive commercial garage door just to toss in a single envelope.
Exactly. Terribly wasteful for battery life. In 5G, with bandwidth parts, the network can talk to your phone and say, look, I have a massive 400 megahertz channel here, but you're just checking email right now. So I want you to only turn on your radio for this tiny 20 megahertz slice of it.
So the phone can just sip from the fire hose instead of drowning in it.
Yes. It can dynamically expand or contract its active bandwidth based on what you're actually doing second by second. That is a game changer for energy efficiency.
Okay, I want to move to the part of this deep dive that genuinely stresses me out just thinking about it.
Uh-oh.
We've talked about these massive pipes and fragmented pieces of spectrum. But how does the actual data survive this process?
You're talking about the protocol stack.
Yeah. I mean, think about the sheer logistics here. I'm downloading a large file. The network splits it into pieces. It sends some pieces over a low frequency, some over a super high frequency. Those radio waves travel at slightly different speeds. They bounce off different buildings, and they arrive at my phone at completely different times. That just sounds like a recipe for a completely corrupted file.
If you didn't have a very, very smart traffic cop in the system, it absolutely would be.
So who is the cop?
It's a layer in the software stack called the MA, Medium Access Control. Think of the MAC layer as the master dispatcher at a giant shipping warehouse.
Okay, let's play this out. I'm the MP layer. I've got 1,000 boxes, which are my data packets, to ship to a phone.
And you have 3 trucks representing 3 component carriers waiting at the loading dock. One is a ridiculously fast sports car, that's band 1. One is a steady, reliable semi-truck, that's band 3. And one is a bicycle courier, band 7.
Okay.
Your job, every single millisecond, is to decide which exact box goes on which vehicle.
We'll just throw them on randomly, whatever's open?
No, you have to be highly strategic. You check the radio quality constantly. You say, oh, the sports car is currently stuck in some interference traffic. Okay, take the priority boxes off the sports car and put them on the semi-truck. This decision-making process happens dynamically, literally thousands of times a second.
But wait, the sports car is still going to get there much faster than the bicycle courier. So box number 50 might arrive at the phone way before box number 10.
Yes. That is known as the out-of-order problem. And that's exactly where the next layer of the stack comes in the RLC, or radio link control. The RLC is the guy standing at your front door with a clipboard.
The receiver on the phone side.
Right. He catches all the boxes. If box 50 arrives first, he doesn't just hand it to the application yet. He holds it in a buffer. He waits for box 10, 11, 12, reassembles them into the perfect original sequence, and only then passes the clean, orderly stream up to YouTube or Netflix.
So when you are watching a perfectly seamless video stream, there's actually this frantic reshuffling happening in a buffer just milliseconds before you see the frame.
Frantic is the exact right word. And it gets even messier. What if a box completely falls off the track? What if a burst of interference kills a packet while it's traveling on the 2.5 gigahertz band?
Doesn't the video just glitch?
Ideally, no. The MASI layer uses something called hybrid ARQ.
Hybrid AR.
Yeah, it's basically a rapid-fire error correction mechanism. If a packet fails, the receiver immediately shouts NACK, not acknowledged.
Okay.
The transmitter hears that and immediately resends just that tiny missing piece. And it often resends it on a completely different, better carrier frequency if the first one was bad.
So it literally swaps trucks mid-delivery.
Basically, yeah. It says, the bicycle dropped the box. Fine, send a duplicate via the semi-truck right now. Go. And this happens so unbelievably fast that the video player and you as the user never even know there was a problem.
It's just the illusion of continuity.
That's the real magic of the protocol stack. It completely hides the violence of the radio environment from the user experience.
Yeah, I love that phrase, the violence of the radio environment. It definitely makes me appreciate what my phone's doing a lot more. But let's bring this back down to the real-world deployments for a second. You mentioned earlier that not all phones can actually do this.
Right, they can't.
If I have a mid-range phone, or maybe a device that's 3 or 4 years old, am I just locked out of this whole highway system?
You might be, or you might just get a very elite version of it. The source documents highlight that the user equipment, your phone, has to explicitly support the specific band combinations that your local network is using.
So if my specific network provider decides to aggregate band 71 and band 4, but the modem chip inside my phone wasn't hardwired to connect those two exact bands,
Then you don't get the aggregation. You just fall back to a single carrier.
Yeah.
You get to ride the bus, but you don't get the train and the taxi. This is actually a massive logistical challenge for phone manufacturers.
because they have to build for everywhere.
Exactly. They have to cram hundreds, maybe thousands of possible global band combinations into a single modem chip so the phone works on networks all over the world.
It really explains why these flagship phones are getting so expensive. The RF engineering inside a modern phone is basically military-grade hardware at this point.
It truly is. And don't forget the antennas. You need physically separate antennas inside the phone for things like 4x4 MIMO on multiple bands at once. It's a literal spatial puzzle trying to fit all that inside a glass chassis that's half an inch thick.
Let's look at the network side again. There's a point in the deployment notes about traffic profiles. It says carrier aggregation is most effective under heavy network load.
Yes.
That seems a bit counterintuitive to me. I think I'd want the massive turbo boost when I'm the only one on the road
Right.
to get those crazy speed test numbers.
Well, think about it from the network operator's perspective. If it's 3 a.m. and you're the only person connected to that tower, a single 20 megahertz carrier is going to give you, say, 150 megabits per second.
Which is plenty fast.
Right, it's plenty. You don't need to aggregate 5 bands just to load a web page or stream a song.
True.
But what about at 5 p.m. rush hour? The bus is totally full, the train is full. That's when aggregation really shines for the operator. It allows the network to constantly load balance everyone.
Oh, I see.
It can look at the traffic and say, okay, the main low band is getting absolutely hammered right now, so let's offload 30% of this user's data to this other high-frequency band over here that's currently empty. It keeps the aggregate throughput high for everybody, even when individual bands are highly congested.
So it's much less about hitting some generic peak speed record for one person and more about raising the floor for everyone so the whole network doesn't collapse under the load.
Exactly. It raises the average baseline user experience.
So zooming out a bit here, we've gone from just expecting magic internet in our Ubers to understanding this incredibly complex dance of fragmented spectrum, massive 5G pipes, and a protocol stack that's juggling packets like a circus performer.
It's a pretty comprehensive and beautiful system when you see it all laid out.
But looking at where this is going, based on the 5G NR specs, 16 carriers, 400 megahertz blocks, we're talking about data pipes that are wider than anything we've ever seen. Is there a physical limit to this?
Well, this actually brings up the most provocative thought for me when looking at all these source documents.
Doctor.
For the last 20 years of mobile technology, the bottleneck has always been the network. You usually had a fast phone, but you were stuck waiting on a slow cellular connection.
Right, just staring at the spinning loading wheel.
But now, if a fully aggregated 5G network can deliver multiple gigabits per second consistently through the air, the bottleneck actually moves. It moves to the device in your hand.
Wait, you mean the phone itself won't be able to keep up with the network?
Think about it. Can your phone's internal flash storage actually write incoming data at 5 gigabits per second? Can the processor decrypt, decode, and render that massive of a video stream in real time without completely melting the battery?
Wow, I hadn't thought about that. We're actually reaching a point where the air is faster than the physical wire inside the phone.
We are getting very close to that line. We might honestly see a future where the network is effectively infinite for the purposes of a handheld device. And the real limitation just becomes how fast can the silicon inside your phone actually think?
That is a wild shift in how we think about tech.
Yeah,
It puts all the pressure right back on the chip manufacturers.
it does. And it completely changes how we might design apps in the future. If the network is instant and massive, maybe you don't even need local storage anymore.
Because you just pull it from the sky instantly.
Right. Maybe the phone becomes just a high-resolution screen and a battery, and the actual computer is entirely in the cloud, streaming the whole interface down to you via carrier aggregation.
So the old mainframe dumb terminal returns just wirelessly.
History tends to rhyme, doesn't it?
It really does. Well, on that note, I think I'm going to look at my little signal bar at the top of my screen a little differently today. It's not just a single bar. It's a whole team of frequencies working overtime.
It is a very hardworking team.
Thanks for breaking this all down with us today.
My pleasure, anytime.
And thank you to everyone listening. Next time you pull down a massive file in seconds while sitting in traffic, just remember the frantic juggling act happening in the invisible layers all around you. This has been The Deep Dive. Catch you next time.